In this video, I'm going to do an overview of this new technical report based on this software engineering agent that was released a couple of weeks or months back. And what we're going to go through is the actual framework that was used and some insights, and also share some of the results that they reported in this paper. At a high level, what they introduced in this paper is this SWE-Agent, an autonomous system that uses a language model to interact with a computer to solve software engineering tasks. So the idea here is that you want to build a system that removes basically a human interaction and basically solves the task using a language model and a framework that allows for interactions with a terminal or interactions with a system to be able to carry out these software engineering tasks. And what they have shown, or what they introduce here, is this agent computer interface, which we are going to get into details in just a few minutes. Overall, the main result was that this agent is able to solve 12.5% of issues compared to previous best of 3.8 achieved with a RAG system. And we go through the details of what this RAG system is and other systems that they compare with. The main focus of this paper is this ACI, this agent computer interface that they're proposing. And the way I understand this is you're essentially creating an interface that allows this LLM-based agent to efficiently and effectively interact with a terminal or a file system to be able to complete this software engineering task. In this paper, what they do is they use this framework called the React. And we talk about the React framework. We actually teach about it in our courses, and what are the different components that you need. And that's basically what they are using here. And this React framework allows a language model to be able to take actions, right? Do some thought processing, and then also make an observation in the environment. And the environment will return a feedback, and that feedback is then considered, and it goes step by step, iterating, figure out what the solution was for that particular task. That's what the React work is about, and you can read about it. We actually have a guide about this as well in our prompting guide. And what they're proposing here is that they want to optimize or design an agent computer interface, which is what's summarized here. Right? Instead of focusing on optimizing the weights of these language models, we're going to focus on creating this interface that allows a smooth interaction between the LLM-based agent and the system that needs to be, or the tools, right? That involves the tools like the terminal and the file system to be able to carry out whatever edits, whatever changes need to happen with the code. What they do is they build this SWE-Agent based on that agent computer interface, right? And they use a GPT-4 Turbo as the base language model. And here they're showing kind of the results. But what's really interesting about this is that they have actually built an interface that really works well with GPT-4 Turbo, and they also reported this here. You can see that this particular SWE agent that they have created also sort of works also using something like Cloud 3 Opus, right, which is a very powerful model with very long context support. And that one can solve 10.5%. It's not as great as GPT-4 Turbo, but I think it's because this one was designed on top of the GPT-4 Turbo model. So let's go through each one of the main components here and some of the interesting bits that this paper proposes. Right, so we know that these language models, right, act as an agent by interacting with the environment, right, through an iterative way, taking actions and receiving feedback. This is basically the React framework being applied here. So if you know about the React framework, right, the model comes up with a thought, right, and then it comes up with an action as well. You can provide it information about what certain actions it has. Once you have that, it combines this kind of thought plus action, and then it gets an observation from the environment. Once it gets that observation, then it has that extra knowledge that it will integrate, and then it will take an additional thought and action, and it goes through this iterative loop until it figures out a solution. So in a way, the agent receives feedback from the command execution in the environment, right? And the environment that we're talking about here is, you can have different environments, but here what matters more is this computer environment, which will be the terminal and your file system. Those are really important, right? Because this particular agent needs access to like the file, the repository, right? And needs to be able to also modify that. And also it should be able to have access to the file system, like if it wants to create a file or edit a file as well. Well, one main thing that's highlighted in this paper, without going into too much details, is that this particular agent computer interface serves as an operator that provides the necessary information to the LLM agent to carry out the task, right? That's what we're seeing here at the top. So the building or designing of this particular interface is really important. So we're going to go through the components that are important for this ACI, framework. There were some observations that were made on what really makes an effective agent-computer interface. There are a couple of things that the authors mentioned. So actions should be simple and easy to understand. And this is about making things simpler because, again, we're not trying to optimize the large language model, we're optimizing the interface, right? And the way we optimize this interface is we want to make it as simple as possible to understand because at the end of the day, we need to give this back to the language model, which might have, constraints in terms of its capabilities around reasoning. So we need to make sure that information that's coming is relevant, right? It's simple to understand and so forth. And now for this particular task, it's important to have, this concise documentation, for example. Number two says actions should be efficient, right? So again, this goes back to the point of simplicity. As you may be doing a lot of operations, you may be taking a lot of actions in an environment, but it could be that all those actions, right, will make the system inefficient. So what we want to do is we want to help the agent actually make progress towards a goal in a single step. So if you do a bad design here, right, you can have many, many, many simple actions, and some that are not even needed, and that will lead usually to this particular system not be able to complete the task. So it's really important that the actions be efficient. Have a minimal set of actions instead of having a bunch of actions and some that won't even be needed. So this is just saying that you need to put a lot of careful attention to how the action set that you're basically enabling in the system. Number three here is environment feedback should be informative. And again, if you are providing the model irrelevant feedback, right? If you're giving it, I don't know, debugging, logging, or logs that are irrelevant, then that won't be useful to the system, right? So you want to make that context that you're providing, that feedback should be as relevant as possible to that particular task, right? To that particular step that the model is taking to complete that task. I don't think this is specific to software engineering specifically. I think this could apply to pretty much any task. One interesting bit that is more specific, I would say, to software engineering is the fourth one, which is guardrails mitigate error propagation. Right. So what we want to do here is we want to be able to handle errors and also apply something like a code syntax checker, right? Like a code linter, for instance, that can help the model kind of, understand this is the particular mistake that was made, and the agent can recognize and then fix those, right? So you can be in a loop, right? This agent can be in a loop trying to fix an error, and it's just going to propagate throughout, and it's going to be costly, and it's just going to take forever to fix the actual problem. And this section 3 is talking about the actual design of the ACI, the agent computer interface, for software engineering specifically. So this might not apply specifically to other types of tasks, but this applies mostly to software engineering tasks, right? I also like that in the paper, they're very transparent about that. They're going to evaluate this particular system, SWE-bench, a benchmark for evaluating LMs on real-world software issues collected from GitHub. The task is basically to, given a code base and a natural language request, such as a feature request, bug report, whatever that may be, generate a code base revision or a patch that passes the unit test, which verifies that the issue has been remedied. So what's going to be measured here, or what's going to be taken as a metric, is if the particular solution, right, provided by this model or revision can pass this unit test and can resolve the problem. Now, solving this task requires performing a number of software engineering subtasks, so like bug localization, which is really important, program repair, and writing tests. So this is why we need access to the file system. We need access to like a terminal, because that's how we're going to be able to kind of complete this task. So all of these things are, again, specific to software engineering tasks. But if you are working in a different domain, a different problem, you might have different subtasks that you are considering in your particular framework. One important note here for this ACI that's being designed. So it says that a well-designed ACI should help the agent understand the state of the repository given the previous changes. It should also help the agent recover from mistakes, remove unnecessary context from prior observations, and suppress any unusual lengthy program outputs. So there's a lot of little design choices that are happening here. What should we provide the model, right? How should the model use certain context, how to optimize that context that we're passing, right? What's the output, what's the feedback that we're passing to this agent? So all of that should be taken into consideration. This was optimized carefully. There's different hyperparameters that were kind of optimized to come up with a good solution. So there are certain configurations here that we need to actually pay attention to. In this particular page, we see the different components of this SWE-Agent interface. Right? So we have search and navigation, which is important, right? To search through files, search directories, and so on. That's kind of typically what you would do if you were to try to solve a task, right? That's that navigation or exploration component is really key for this agent, and that's what is mentioned here. And interesting, they say that if a search produces more than 50 results, they do not report the results and instead suggest to the agent to write a more specific query. So again, that has to do with providing the relevant context. You have the limitation of context length and also understanding longer context as well with these models. So it's important to consider these choices when you're building your own agent. There's also file viewer, file editor, context management. File viewer is again trying to figure out what file to open and so forth, right? That's about navigation. File editing is obviously there needs to be some patching that goes on, right? If the model finds a mistake, what is the patching? What's the edit that happens? And there's going to be a lot of editing that's happening, obviously, if you want to fix a certain issue, right? If you're patching some code or fixing an issue in this code. So this is an important one to have access to as well. And what you see here is these different commands: scroll up, scroll down, edit, and so forth for different components like search directory and so on, which this model has access to. If you look at the example here at the top, see that these are special commands: open, search, dir, edit, of edit, and so forth. And here's a more clear example, I would say. So the file viewer, right, it shows like in what context, right, these particular lines lie on. So it's like there's 400 lines above and 2,684 lines below. So that's really important context for or information for the model to have, and that's part of the observation. And in terms of the response, right, you have when you're doing editing, you can see here how it's also presenting the lines. All that contextual information is really key for the model to have access to. So you can read more about it. I think one of the most important components of this, I would say file editor, file viewer, it's not surprising to me. The navigation and search, we notice that the more we try to optimize these models with some type of search component, is basically we're trying to guide the model better, right? Provide better guidance. So I think this is a general type of insight that we're seeing from these models, right? The ability to search better for relevant information that's needed as context. But I think the most important part of this work is this context management. You can have all that information. You can provide all, the file editor. These commands can be well explained. The model maybe knows what command to take on and has a good understanding of this particular domain. But if you're not passing the right information, you won't get the right results with these models, right? We know that. Basically, the idea of prompt engineering is basically that you try to optimize the context as much as possible to your particular task. And this is where all of that applies. So if you're passing the model, in this case, with a software engineering task, the error messages, the history processors, right, to keep the agent context concise and informative. It's about conciseness and making sure it's informative, right? Any additional information you're passing to the model, and in this case, there can be a lot of irrelevant information, right? Because you are interacting with this external environment, right? Which could be a terminal, could be something like that, that provides like logs, all these logs that you can even understand, and you're just feeding that back to the model, that won't really give you the results that you want. And you have to manage the context a little bit better to be able to deal with errors, to be able to fix the solutions fast. That's basically what this context management is about. Here are the experiments, and this is the experimental setup. So we have the data sets, the SWE-bench data set, right, which includes 2.2K task instances from 12 different repositories of popular Python packages. And we're focusing on Python here. That's something to note as well, because that shows you this one is particularly constrained on Python, but it might not transfer over to a different language like Go or Ruby and so forth, right? So just keep that in mind. The results may vary. And their models, the main model was used is GPT-4 and Cloud 3 Opus. Obviously, they got better results with GPT-4 Turbo because they were optimizing and making configuration decisions based on that model in particular. And other models that were tried were Llama 3 and DeepSeek Coder, which are also very powerful models. And one question I had earlier when Llama 3 was released, how good is it at actual code generation? It turns out that for this particular task, it's not as great. And that has to do with the context window limitation. But I think it also has to do with the fact that this is a general purpose model that might have not seen so much code data, or it's not really tuned to do code generation really well. But it's important, right? If it's a general purpose model, it's important that it's able to reason about this particular task and be able to perform this task. That's something that, probably we'll see a lot more better results and systems and different ideas proposed to improve, even the smaller models as well on this particular kind of agentic workflows that we're building. So there are two basins that were used here, which is this RAG system and this shell-only system. And this shell-only system, it basically involves an interactive basin system, which asks the LLM to resolve the issue by interacting with shell process on Linux. And the SWE-Agent involves this agent computer interface that was built with all the different functionalities and access to different tools that are needed to solve the task. And the metrics that were used here are percentage resolved and average cost. The main result is here. You can see with the RAG system, the shell-only agent, and then we have an SWE agent, right? GPT-4 Turbo and Cloud 3 Opus was used. This one, you can see how it performs on the different benchmarks. So for SWE bench, which is the main result here, we have 12.47, but also for the benchlight, we have 18.0 as well, using GPT-4 Turbo. And here are some results of the different components, right? And it says, the importance of all these different components like the editor, search, file viewer, context, right? And you can see how for this little cowboy hat emoji here, that's the best result, right? And we talk about different search solutions in a bit, but the editor with the linting on gives you the best result here, right? And this summarization summarized search gives you the best. There's different search that you can use as well. You can do iterative search, which is shown here. An example of it is provided here, which, you use this kind of next previous search result. It's like basically trying to mimic like VS Code. If you have search for something, you get these pages and then you can go next, next, next. And the model has access to that, right? You can use that command to go next or to go back or previous and so forth. That's kind of iterative. But you can imagine if you're doing that, you can be going through like 100 different pages of search results, and that could get, pretty like long to process. And so that could be very inefficient. But if you're summarizing it, right, you can potentially even use another language model to summarize and enhance this search. But if you can summarize that, give all the results in one single output, then I think that's a more efficient way to do this. And that's what they show with the summarized search version. They also show shell-only results here as well, how the performance drops compared to the main result here. File viewer as well. Interesting here, like, you may think, the more information you provide the model, the better the results. But it turns out that there's kind of like a good amount of information that's good enough for the system. And if you give it too much, right, you're essentially adding a lot of noise. This is something I always talk about with language models, that you're trying to optimize the context. And by doing so, you may think providing more and more and more additional context, will lead to better performance. But that's not always the case. And this seems to be the case as well with this particular task, that there's kind of a really ideal number of lines that you want to pass. Says if you're providing full history, the performance goes down. And if you provide it with demonstrations, you can see. So providing relevant context is key here. So this one says human user interfaces are not always suitable as agent computer interfaces. This is a really important point because we want to make these models work with any environment and interact with any tool. But the fact of the matter is that, you know, those systems that we have built and those tools that we have built, we have optimized them for humans, right? For human usage. And so, as an example, if you were to use, the shell-only environment that interacts with this terminal, right? You have access to commands like cd, ls, and cat. Those will give you some output, and the language model can leverage those outputs. But it turns out that the information that you're getting from these particular commands very inefficient, according to this study. And you can also use something like grep and find, and there might be other clever and more efficient ways on how you interact with the terminal to get access to information than to fix things, right? And it says that if you do that, you might get better results, right? But usually there's a lot of irrelevant information that you're introducing as well. So you have that problem of introducing too much noise and less signal. So they are hypothesizing that better localization is possible with faster navigation and a more informative search interface. So here, there's a lot of potential, right? As I mentioned, the idea of using the shell-only search versus iterative search versus summarized search, right? So we have to kind of differentiate like how we feed information or how the language model should optimally use the information and optimally interact with tools as, compared to how maybe a human interact with tools and the interfaces that humans have access to and how they interact with those tools. This again goes through some examples when you're using, I mentioned the idea of using linting, right? Like a code linter also helps especially with the editing component, right? Because giving the model that signal, whether there was an error, a minor error or maybe a major error in the changes, right, of the code, that's really important for the system to have. Because that will determine, how effective that system is at completing the particular coding task. Here's just a deeper analysis into the agent behavior, and there are a couple of things that were highlighted here, which are these, which they see as consistent problem-solving patterns that emerge when LMs are equipped with a useful, intuitive agent-computer interface. So there is idea of reproduction or localization in the first step. So localization, right? So what are kind of the patterns that these agents are using to solve or resolve these particular tasks that they were given, right? Software engineering tasks. In terms of, there are a couple of interesting patterns here, and this table summarizes basically the most common patterns, right? Which is like editing, 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 and this has to do with reproduction, right? Because there's obviously going to be reproduction of code that's happening here because it's obviously trying to fix these issues in this code, this specific code base. And then there's also, like, you can see create, edit Python as well. Edit Python RM, edit Python edit. So there's a lot of like in combination, edit in combination with create, right? And that has to do with reproduction. And then localization has to do with more like, finding information, searching directories, searching files, and so forth. And you can see that also that's a very common pattern here. This particular chart is interesting. It says that a majority of turns are spent editing, right? I just mentioned that. But after turn 5 and onwards, right? Remember, this is an iterative, system, right? After turn 5, you can see that it's spending most of its time, right, on two actions, which is edit and Python. So it's, just using these edit and Python. You can also see it here from the table, right? Edit and Python is using those a lot to actually fix the problem, right? So it's trying. What I understood from this is trying to like really get to a solution as fast as possible, and that's something that is highlighted here as well, right? And that's where the question of can the system find a really optimal path or optimal pattern of commands, right, or actions that it can take to solve the problem. Ideally, that would be something that this model can figure out really quickly to do. That would entail potentially, right, having to tune these models on this particular domain. This wasn't done in this study, right? But that's something I would have want to see as well, if there's any kind of improvements that can come from that. Just giving it more knowledge, or training it or tuning it on more knowledge like that. I think that would be an interesting experiment too. But I also like that they didn't do that, because they're optimizing and getting the most that they can get from this, from keeping the model fixed, right? Keeping the language model fixed. And they also mention here, agents succeed fast and fail slowly. This is an interesting insight, I think. What they're finding out is that they find that runs submitted relatively early are much more likely to be successful compared to runs submitted after a large number of steps or calls. And I think this has to do with the fact that providing all that unnecessary context that you might not even need, right? You may think, oh, if this model is giving more and more context, or it does perform more steps, that it will, potentially solve the problem. But it turns out that it actually fails a lot of the time if it's taking too long. And those are good hints to have, because that could save you in terms of cost. That could maybe give insights to this model if it had some kind of meta prompt or meta component that's looking at it and it's monitoring its behavior and how it's dealing with that particular task, and how it's trying to implement it, and how fast it is, right? It's solving specific parts of the problem. So I think that's an interesting insight as well. I think there's more potential to do deeper analysis here, but that's something that you should definitely take a look at, and they report some results. And just want to mention that you can take a look at table 10. There's a huge appendix here. They do a lot of different analysis and so forth. There's a ton of pages here, with so many results, like how they handle errors, right? And how they're passing information, what's the template that they use as well, because this is an agentic workflow and they're using React. So all of those components, right? There's a lot of results here that I won't be able to go through in this video, but do take a look at that. My hope is that this was interesting to you, and that it can provide you some insights if you're building agentic workflows. My takeaways of this paper is that the importance of that context management, I think that's really key here. Like, you have all this information from this environment that you're getting as feedback. You have all this information, right, from the actual code base as well, how you're passing that information in an optimal way. That's really key for the system. The rest of stuff like React, the file editor, the file viewer, the search and navigation, I think are easy to figure out. And yes, it will involve some kind of experimentation, or maybe additional experiments on what are the type of actions you want to give them all, and so on. The React framework is very intuitive to understand. I do encourage everyone, if they're interested in building agentic workflows, to actually look at the React paper. It does provide a lot of good insights into actually building these type of agentic systems. And I like that they kept it really simple and they used the React framework, right? Because they could have chosen to use some other more modern version of that, which there are so many variants of React today. I think it makes the paper easier to understand and so forth. So a lot of potential in this paper. The metrics also could be different as well. They could also try to enhance the SWE-bench test set, because you could include different programming languages to see if all of this approach actually generalizes. What types of problems as well, what are the software engineering tasks? Does something like this actually, generalizes as well to other frameworks, other types of software engineering tasks, right, and so forth. So all of those are kind of questions that I have in mind, and I think from here, we will see more work around using agents for software engineering tasks. So I'm very, very excited about that, and hopefully this video gave you some insight and idea on what's happening with the space, what are people interested in, and so forth. Okay, that will be it for the video. Please consider leaving a like. That gives me a signal whether you're enjoying these videos and this format is useful. And please subscribe also to the channel. That also kind of helps the channel, and it tells me that you want to see more of this type of content. Have a good one.